Hello, everyone. My name is XCaliber, and I am a graduate student in the US. I'm doing a PhD in physics. I have been a graduate research assistant since 2021, and I was a TA for 2 years before that. A few disclaimers about this talk. This is a scientific talk, so there will be science in here. But I have just assumed that none of you have heard any of this before, so there's no prerequisite knowledge. I have kept math completely out. If there are any numbers, it's just as facts. And if I'm showing any graphs, it's either there to just look pretty or I'll explain what things are. A brief history about what I've done. My undergrad is in electrical engineering and instrumentation science. I did it in India and I graduated in 2017. Then around my third year, so junior year, I realized that I hate engineering and I didn't want to do a 9 to 5 job. So I started pivoting towards research and I wanted to become a scientist. So instead of getting a job after graduating, I worked at a lab as a research assistant for 2 years, and then I moved to the US to do a PhD in physics. Okay, so what do I do exactly? My work mostly is I set up tabletop optics experiments. If I design my own experiments, depending on what I'm doing and what measurements I'm making. Like, for example, on the right image, you see a mirror. I do coating thermal noise measurements for these mirror coatings. These mirrors have very shiny, polished coatings, which make them extremely reflective to some laser lights. And I measure the thermal noise on them. I also work on cameras. In fact, right now, my latest project is I'm working on a CCD phase camera, which can look at laser spot size and see deformations in the spot, which occur due to defects in the mirrors. And probably the most fun thing I work on is lasers. Nice typing. I work on a bunch of lasers. I make my own lasers. Most of the lasers are actually invisible. I work with 1064 nanometers and 2 micron. We do have 532, which is green lasers, but that's mostly to do with diagnostics, and we don't actually do any science with it. Next slide. So these are just some random basic images I grabbed, which kind of summarize what LIGO is. So LIGO stands for Laser Interferometer Gravitational Wave Observatory. It's less of an observatory and more of a detector. It has a laser, hence the L laser. It's an interferometer. If you don't know what an interferometer is, I'll explain it a little bit, but you can ask me in Q&A for a detailed explanation. The graph on the bottom left, bottom right side is just data that we actually get of gravitational wave signals. The image above that is a very simple optical layout of what the interferometer looks like from top. The image on the middle top is the actual LIGO detector in Livingston, Louisiana. It's one of the two detectors US has. The image below that is our pendulum suspension. The image to the left, which looks like two cylinders, those are our test masses. These are heavy fused silica mirrors, each weighing around 30 to 40 kilograms each. And yeah, and that I'll ignore the top left image. Next slide, please. Okay, so what are gravitational waves? Now, well, they are waves in gravity, but the explanation is a little more complicated than that. So can you go to the next slide? Let me see if I can compress like 100 years worth of physics in a slide. So you all know this guy. That's Albert Einstein. The most famous thing he's known for is probably relativity. Fun fact, by the way, he did not actually get the Nobel Prize for relativity. He got it for his explanation of photoelectric effect. And one of the fun jokes we used to say in high school was that relativity was too complicated for the Nobel Committee. So they gave it to him for something that they could understand. But yeah, he discovered, well, not discovered, he invented relativity because it's like a theory. And there are two branches to relativity. There's special relativity and general relativity. A very quick overview of what the difference between two is. Special relativity is related to things like time dilation, length contraction, Lorentz transformation of your fancy words, which you don't need to bother about. Basically, if you move at very high speeds, almost comparable to the speed of light, how does the world change around you? That's special relativity. And some of the results or implications of special relativity are like the things I told you. And one of the biggest is, well, the famous E equals mc square equation that comes from special relativity. And the other is the fact that time also kind of shows up as a dimension. So we are all familiar with the three dimensions, which is up, down, left, right, front, back. But time also in Einstein's equations kind of manifests itself as a dimension. And that's where the term fourth dimension or space-time comes into picture. And then with this special relativity, if you start thinking about gravity, Einstein, there are a couple thought experiments that I can uh, talk to you about in Q&A if you're interested. But basically, Einstein kind of realized that gravity isn't really a thing. Uh, a lot of conspiracy theorists would probably rejoice at that. But basically, gravity manifests itself as a force, air quotes force, because of how things move in curved spacetime. And that is what general relativity handles. And that's like an extension of special relativity when you try to explain gravity. Basic idea is that this four-dimensional spacetime that we have is not flat, it's curved, and things appear to move as if they are affected by a force when they are going through this curved spacetime. Some of the things that general relativity predicts or implies are things like clocks moving slower if they are like they are orbiting Earth further away than they are closer to us. This is a thing that actually has to be used in GPS satellites to make sure that the times are in sync. Then there are things like light bending, because Newtonian mechanics does not explain or does not say that light should bend because of gravity, but general relativity does. And that's what you can see around the black hole. This is not a real image, it's an artist rendition, but still, like light actually does bend. You can see it during solar eclipse. Stars which are supposed to be behind the sun show up beside the sun because the light is bending around the sun. And the other thing that general relativity, the equations of general relativity predict are gravitational waves. And the basic idea is that they are waves in this 4D space-time continuum that we have. They're just ripples and disturbances that propagate. Next slide, please. Oh, this is a bunch of images. You might want to just spam them a few times. So yeah, there are ripples in space-time, four-dimensional space-time. And just like if you have a still lake and there's water in it and nothing's moving, if you put your hand in and move it around, you're going to cause disturbances and waves and stuff that like flow out. It's very similar to that. The things that cause gravitational waves are anything that's moving and has mass. So technically, you just waving your hands, you are generating gravitational waves. The problem with that is if you actually do the numbers and try to calculate what the strength of these waves will be, they are stupidly low, almost zero, right? No chance of detecting them. To increase the strength of these waves, you need one, really heavy things, and two, very fast moving things. So we have heavy things, stars are pretty heavy, but generally they don't move as fast as we want them to. So we don't see a lot of gravitational wave sources. Now, under very special circumstances, they do move fast, and we kind of have theoretically categorized four sources of gravitational waves. The first are very simple, supernova, right? When a star uh, becomes as old as Atriarch, it goes boom. If it is big enough, it goes boom. But that explosion is heavy enough that it's massive enough that the waves are strong, and it's an explosion. It's an instantaneous, violent explosion. So it's fast enough that it will create gravitational waves. We call these burst events because they're a burst, instant, like a sharp peak of signal and then nothing else. The second type, which is the most interesting and which what we actually detect, are what we call compact binary coalescence. It's just a fancy term for two things rotating around each other. And these two things can be stars. But turns out stars are so big that when they're rotating around each other, they are just too slow. So you have to kind of push them closer so that they start spinning faster, but they can't get close enough before they touch to spin fast enough. So we need small stars but heavy stars. And we have those. They are called neutron stars and black holes. Neutron stars are just the remnants of a supernova. It's a very dense, it's pure neutrons. It's like a teaspoon of neutron star material weighs like millions of kilograms. In fact, I remember a fun fact. If the sun becomes a neutron star, the star will fit inside Chicago. That's how dense it is. So the whole mass of the star compressed inside the city of Chicago. So when you have something that dense and that small, you can get really close. And when you're that close, you spin really fast. And this meets both the criteria of generating strong gravitational waves. And black holes are just better. Black holes are smaller and generally heavier than neutron stars. So they create even stronger gravitational fields. The GIF on the bottom left side, you see that's an artist's rendition of two black holes like merging. We call it a merger. They're merging. They initially spin around, slowly come closer. The closer they come, they start spinning faster. Then they merge, and then there's a ring down. So they become one black hole. The image on the top right side kind of shows you how the waves look like as they are slowly spinning in the beginning. It's a constant wave, like sine wave type of thing that goes out. As they come closer, the frequency increases, the amplitude also increases, and then they merge. But that's not actually how the wave looks. It's just an intuitive understanding of the wave. If you actually were to stand near these two black holes and look at it, and if you hold a hula hoop in front of you, the white GIF is how the hula hoop would actually flex as the gravitational wave comes behind. So, and then if you draw that same flexing in like a direction the wave is traveling, that's what you get in the bottom right side. So that's actually how the gravitational wave looks as it is moving outwards from these sources. Next slide, please. Okay, so the next slide is a video. Now, I showed you how that hula hoop flexes, right? Now, how do we detect gravitational waves? So imagine this, don't play the video right now. This is what we call an interferometer. It's just a big L where light comes from the source, which is the cylinder on the bottom left side. It gets split by a mirror into two, goes off in two perpendicular directions, hits mirrors and comes back. And when it comes back, the experiment is designed in such a way that the light interferes. And normally, when nothing's moving, it interferes destructively, and there's no light on the sensor, which is the square thing on the bottom right side. Now, imagine this L, but it's inside that hula hoop. Now, as that hula hoop is flexing, compressing and stretching on different sides, these mirrors will move. And as they move, they change the interference condition on the return path. And that causes the light to change in brightness. And that's what we detect. So now you can play the video, and this is just a cool animation that shows exactly what happens. Oh, wait, you might not. Oh, the Google slides. Wait, I'll send you the link. Can I right click link this? No, I can't. I just look it up on Google. Actually, you know what? I'll show this at the end. You can skip this for now. Next slide. Remind me to play this video once. Okay, this is a scary plot. Click once more. This is supposed to be. Oh, it plays nice. All right, here the zoomers will be happy now. So this curve is what we call a noise budget. It You don't need to worry anything about it. All I need you to look at is the orange and the green lines, which are in the middle. It's like a kind of a U shape. They so these plots show us what noise we have in the sensor. So if we have a signal which is above this U shape, that we can see because it's above the noise. If it's below, we won't be able to see it. So the orange and the green are our total measured noise. They are squeezed and unsqueezed. I won't talk about what squeezing is, but if you trace the well of that curve, if you trace on the left side and see what the axis on the y-axis it shows up as, it's around 10 to the negative 23, right? And the units are strain. So strain is, if you have taken any physics course, it's change in length divided by length. So if you have a strain and you multiply it by length, you get the change in length. Now, the length of these L-shaped arms that I showed in the image before, those are the length of our interferometer arms. Those are 4 kilometer long arms that just go out 4 kilometers away and then come back. So our arm length is 4 kilometers. Not only that, we have fancy stuff happening in these arms where the light bounces multiple times, bounces around 250 times. So effectively, our arm length is 4 times 250, which is like 1,000 kilometers. Yeah. So 1,000 kilometers is like 10 to the 6 meters. So if you multiply 10 to the 6 with this 10 to the negative 23 strain, that gives you the change in length that we are measuring, which is 10 to the negative 17. Now, to give you how small 10 to the negative 17 meters is, 1 micrometer is 10 to the negative 6. So that's like bacteria, human cells, and stuff. If you go 1,000 times smaller than that, 10 to the negative 9 is DNA, diameter of DNA, and then you start seeing like atomic structures. 10 to the negative 10 is how big atoms are. Then you go another like what is that? 10 to the 5. So another 10,000 times smaller than the size of an atom is a proton. So that's 10 to the negative 15, which is a fermimeter, I believe. That's the diameter of a proton, which is the positive charges at the center of a nucleus of an atom. This is 100 times smaller than the diameter of a proton. That's the length change we are measuring. So LIGO detectors, like we say that these are the world's most precise rulers. That's basically what we have built to measure these tiny changes in distance, which the mirrors move. Next slide, please. There's nothing. Oh, yeah, images. Yeah, just click them a few times. So these are what the gravitational signals actually look like. Remember, I had said that the stars kind of like just start off smoothly spinning around each other. So if you look at the bottom left graph, that's the left part of the graph where it's kind of like a constant sine wave. That's called the inspiral phase. Then as this come close together, the frequency increases, they speed up, amplitude increases, and then they merge, they join together. That's the middle part where it's called a merger, the arrow points towards it. And then ring down is when they have kind of like become one mass and then they like spin a few times and settle down, and then there's no gravitational wave. So that's the ring down. Now, that the bottom left image is what theoretically like our mathematical models predict, but that's not what you're going to measure. There's always going to be noise. So the top right images are what we actually measure. So at the top row, we have the left and the right. Those are the Hanford and Livingston data, the two detector sites that we have in the US. But you can still kind of make out the similar shape that the bottom left graph has with noise attached. The second row below that is our fitted data. So we use this model and then fit that data. And then below that, the third row is the noise, which you subtract. So basically, if you add the second and the third rows, you should get the first one. The last, that blue image is just a fancy way of visualizing the signal. You can kind of see like that curve, which is in yellow green. That's our signal. There were a few sound clips, but I don't think these will work. So these frequencies of these signals just happen to be in the range of the human audio frequencies, right? They are between 20 to 20,000, not to 20,000, like 20 to 2,000 hertz, and humans can hear that. So technically, if you take the signal and plug it into a speaker or a headphone, you can hear the sound, and it sounds like a whoop signal. And for some reason, someone that reminded someone of birds. So this signal is called the chirp. It's called the gravitational wave chirp. Next slide, please. I'll send these clips to Jester so we can listen to this later on. Why do we want to measure these though, right? Like who cares when two black holes like spin and merge? somewhere in the distance. Like it's not affecting us. The length it changes is like nothing almost. So why do we need to measure these? So let's talk about like human senses, right? Humans have generally five senses. Only one of them actually lets us see stars, which are our eyes. We can't hear, smell, touch, or lick the stars. Um, so that's what we started with. Like ancient Greeks just looked up in the sky and started drawing with the stars. And then Galileo invented the telescope, found a few planets. Then we built bigger telescopes, which were land based. We also found out that the visible frequency is not all of light. Light has frequencies above and below it as well. Then we started imaging infrared and ultraviolet light. Then we realized clouds suck. So we sent uh, satellites, which are telescopes. The top middle is Hubble, uh, still operational today. Uh, and then after visible, we kind of realized that stars do a lot of other things. The antenna with the mirrors in the middle is a gamma ray detector. I think it's called MAGIC. I don't remember what it stands for, but it detects gamma rays. Then we have a gamma ray detector in space called Fermi. It's a satellite. If you click a few more times, just and then oh yeah, and then so top right side is James Webb telescopes, which people might have heard. That's one of our latest detectors we have outside. It's also ENM, electromagnetic waves, but I think it also has some particle detectors. There's the bottom right image is a huge neutrino detector that's in Japan. It's called Super K. It detects neutrinos coming from space. Periyagor Observatory also does high energy cosmic rays. So now we are detecting particles, right? Not just light. And this is basically the start of what is known as multi-messenger astronomy, where we are not just looking at light. We are looking at different other sources, other things that like comes to us from space. And one of those things is gravitational waves. Next slide, please. So yeah, and that's gravitational waves, right? This is the image of the LIGO Hanford Observatory. You can see the 4 kilometer long arms that I mentioned. Uh, uh, and yeah, it's just this is probably the third thing that we have found that comes from stars after light and particles. And one of the biggest advantages of these detectors are they are the only ones that can measure things happening with black holes, because black holes don't normally send out light or any particles. There are Hawking radiations, but we have like measured them. That's still theoretical. But these are actually direct measurements of things that black holes are doing. So that's unique about gravitational waves. Next slide. All right. So these are okay. Before that, the reason I said that LIGO is less of an observatory and more of a detector is because it's like ears and not exactly eye. Like eyes are more like observatories, right? You point a telescope towards the star and you look at the star. That's how what your eyes do. Uh, LIGO is more like ears. They just listen to these signals from everywhere. And just like ears, if you have two or multiple of them, you can figure out what direction the sound is coming from, just like how your brain calculates that with two ears. So because of that, we have multiple detectors. US has two. Hanford is the top left image in a desert in Washington. Livingston, Louisiana has the second one in the US. Then the four images on the right side, top left is also Hanford. Top right is Kagra, which is a Japanese detector. It's a 3 kilometer long detector, but it's cryogenic. So they operate at a much lower temperature and it's underground. It's under like a mountain. In fact, I think it's in the same facility as the neutrino detector that I showed in the previous slide. Bottom right side is again Livingston, Louisiana, and bottom left is Virgo, which is the European detector. That's also 3 kilometer long. And you can see the relative positions on the Earth, the world map on the left. LIGO India is currently under construction. It's supposed to be the third arm of the two LIGO detectors in the US. The idea is you have two detectors kind of close by, and you put the third detector on the opposite corner of the opposite end of the Earth, so that you have like a short distance comparison and a long distance comparison. So that's supposed to come up in like 2030. And the other images are, so the center small image is actually Kagra. You can see it's inside the cave. It's a abandoned mining cave that they built it under. And the other images are just stuff I found uh, of like the LIGO detectors. There's the mirrors, people with PPE. Next slide. Okay, now this here I will show some of the interesting events that we have detected with LIGO. The first one, so this is called GW150914. The nomenclature is the first two numbers are the years, the second two are the month, and the last two are the date. So this was a signal that arrived in 14th of 9, January, February, March, April, May, June, July, September, 14 September 2015. This was, in fact, the first detection we had. This is two black holes merging. On the right side of there's a chart that we always make, which just has like data about the two black holes and like other fun stuff. Some of the things to note are like the distances. This is 1 to 2 giga light years away. I don't even know how if that is a lot of long distance or not. The mass of the two black holes. So there's a primary black hole and secondary black hole. So this is 30 to 40 times the mass of the Earth, mass of the Sun, and the other black hole is 25 to 33. Then on the second column, you see peak displacement of interferometer arms is 0.0002 femtometers. That's the number I was talking about. So femtometer is 1 femtometer is approximately a proton. So this is like 1,000 times smaller than a proton is the length that we measured. At the last of that same block, you see radiated gravitational wave energy. That is the amount of energy that was given out in this event. Now, if you remember from E equals mc squared, we have energy is mass, and then you can convert mass into energy. And that's what a nuclear bomb does. It just destroys a little bit of mass and gives you energy. This is, in this event, 2.5 to 3.5 suns were destroyed. And that much of energy was like thrown out. So these are literally the most powerful events that are happening in our universe. These mergers and supernovas and things like that. The graph in the middle you have already seen. The previous curve was of this same signal. The bottom left image is what we call a sky localization map. Since we have two detectors, we can use them like ears and like mark out a region in the sky where we think the signal is coming from. But in this case, it doesn't really matter. It's two black holes combining. You can't see anything. The gravitational wave signals is all that we get. Next slide. This is slightly more interesting. This is merger of a neutron star and black hole. So one of them is a neutron star and the other one is a black hole. Also not a lot of interesting stuff. The only thing I can point out is if you look at the center plots and you remember that there was like yellow colored C shape in the previous curve, you can almost see nothing here. So this signal was very, very weak. The only way you can see it with your eye, well, you can't see it with your eyes, even on a plot like this. It has to go through computation and stuff. And another fun thing about this is this, well, first of all, this signal arrived 10 days apart. If you look at the name, one arrived 15th Jan on 2020, and the other arrived 5th January of 2020. So only 10 days apart. Sadly, on 5th Jan, the Hanford detector was offline. I think they lost log. They had some technical problems. So they were offline. So we only detected the signal with Livingston and Virgo in EU. And the image on the extreme left bottom, that's sky localization, you will see the top image is much bigger. There's a lot of red areas. That's because with two detectors, you can't narrow down the region by a lot, right? So that's why we have like a big region where we think this event might have happened. But on 15th Jan, all three detectors were online. We detected it all three. And you can see that the localization of that, which is below the other one, is much narrower. So you can pinpoint with more accuracy where you think the event might be. We still didn't see anything in electromagnetic or anything because one of them is a black hole. It just eats everything up. Next slide. Now, this is probably the most significant detection that we had. This is two neutron stars combining. So there's no black holes here. Now, when two neutron stars collide with each other, we expect to see something in the other areas of multi-messenger astronomy, right? So we detected this, and you can see on the info chart there, initial astrometric alert latency. Within 27 minutes of getting the signal, we sent out an alert to everyone in the collaboration that there's probably like two neutron stars have probably collided. We had all three detectors online, so we had a very good sky localization, which is that tiny yellow region you see in the circular plot in the middle, and we could just tell all of our interferometers and everyone, observatories and everyone to point towards that area of the sky and start looking. And we saw it. The image on the left side, that's an image from Hubble, I believe. And on the top right side is a zoomed view where you can see the light slowly dimming down. On like, we saw the signal in 17th August, 22nd August, it's a decent bright spot, and then 26, it's a little less, 28, it's even less. So we have very little time. We have like a week or so to observe these events. And we also observed gamma rays. So the plot in the middle bottom side, those are plots at the top from Fermi, at the bottom from Integral, which are two gamma ray satellites. They detected gamma ray spikes just after this event. So we are pretty sure that this event is what caused these, because they are like they correlate very well. This merger basically proved that multi-messenger astronomy is possible and our systems are decent enough. There's a lot of fun stories I can, because I have been in the collaboration for all of these. So if you're interested in the Q&A, I have like fun stories about these. But for time's sake, let's move on. Next slide, please. Oh, this is what we publish after every observation run. So the way our detectors work is we go inside the detector for like 2 months, and then we work on it, what we call commissioning. We make upgrades, we change things that are not working, we repair stuff, basically work on the detector by hand for 2 months or so, and then we close it, and then we start running it. And we observe for a long time, like 8 to 9 months, 10 months. And those are called observation runs. And then we close down again, do upgrades and maintenance, and then we start observing again. So after every observation run, we produce what's called a catalog, which is just a collection of all the events that we have seen. The way you read these are the two dots at the bottom of each line. If you zoom in, are the two things that are merging. So the blue ones are black holes. If you go to the left, those are the masses of the black holes, and the dot that's the arrow is pointing towards, that's the resultant mass. This is just like a very neat way of showing like 8 months of data. Next slide, please. Okay, future. So we have two detectors in the US. We have like two other detectors, three possibly soon. So we have like 5 detectors in the world, like in very soon. But what are the future plans, right? So if you remember, I had said that we have 4 sources of gravitational waves. By so far, we only measure one, which is the circling things, compact binary black holes or neutron stars. That too, not that well. Our detectors are not great. We observe like maybe 100 or so events every observation run. An observation run lasts like 6, 8, 10 months, whether something breaks or not. And so to observe other sources, for example, supernovas are very quick. So they require high frequency detectors. So to do that, the US has planned a 40-kilometer detector, which is 10 times bigger. It's called Cosmic Explorer. We are very like early stages of that planning. Similarly, EU has the Einstein telescope, which is they're going a bit fancier. They have like a triangular shaped detector, which is the bottom left image, and they plan to have 6 detectors in the same area. And then EU also has LISA, which very recently got funded, I think like a few days ago. And it's supposed to be 3 satellites that they will place in 3 Lagrangian points around the sun. Lagrangian points are points which don't move relative to each other. And it's just going to form like an interferometer, which is like millions of kilometers in size. And that will be able to see much slower signals. So some of the signals are just neutron stars that have like a mountain or something on top of them and they're spinning. So that also produces gravitational waves, but that's too slow for our detectors to measure it. So LISA is supposed to measure that. So there are plans for future detectors as well. But these things are very expensive. LIGO, the two LIGO projects itself are, I think they were like $3 billion or $4 billion each. And wait, not each, the whole thing. And Cosmic Explorer is going to be like, if not 10 times, it's also going to be very expensive. Einstein Telescope even more because they decided to go underground with it. And LISA, I don't even know. LISA somehow got funded before they had like a valid plan and design of the satellites itself. But yeah, so that's the future of gravitational waves. It's a very, very, very young field. It's only been a couple of years since we've had like our first detections. But I think that's the last slide, Chester, right? If I'm not wrong. Oh yeah, it is. Okay, perfect. So with that, I guess that's the end of the talk. And I'll take any questions if there are any.
So,
We had the videos.
oh, that's right. Can you send them in the Discord
Yes,
chat?
while we are waiting for questions, I'll
You can see
send you
them.
the link.
Yeah, the lecture chat. Send them in the lecture chat.
Sure.
First of all, I just want to clarify. You're measuring with those massive arms. You're measuring how it flexes.
Yeah.
That's really cool. I'm going to invite High Potential up here to ask a question.
Oh, there it is. Okay, so I have this link.
Hi, High Potential.
Hi there. Can you hear me?
Yes, we can.
Yes.
Hey there, XCaliber. Thank you for
Oh.
the talk. Really, really fascinating, man. Really
You're welcome.
appreciate it. I had a kind of a specific question about the interferometer that you were using. From the looks of it, it kind of looked like the design was derived off of like a Michelson.
Yes, you're right. It's a Michelson interferometer.
I was curious what material beam splitter was being used there, so you had a good bandpass for the kind of sensitivity you were going for.
So the laser we use is 1064. The beam splitter is the body is made up of fused silica.
Oh, okay.
And the coating is damn it, what's the coating? I keep remembering the coatings I'm measuring, but we have Tantala titanium. I think that's the coating we are using right now. But there are like this is supposed to be like the second generation. Third generation, we plan to use a coating called AlGas, which is aluminium gallium arsenide doped.
Okay, that's a fun
and
one.
these are coatings specifically made that they have extremely low losses for 1064 nanometer light in room temperature.
Okay, so
And
you're
all of
really
this is in the
specified
vacuum.
yeah, okay, you're really specified on that 1080 area as opposed to having the most kind
Yes,
of
exactly. So we use a laser. This is not just any light source.
Right.
It's a very highly stabilized laser. So if you plot its frequency like line spectrum, it's a very sharp line. So it's almost a single wavelength light source.
Oh, like how close are we talking? Like how wide is the band, just for perspective?
Ooh, actually, I don't remember the number off the top of my head.
Okay, I'm used to working with imaging spectrometers, so that's why I was thinking in terms of wide band pass.
So after this talk, I can send you the line width in like 5-10 minutes. I'll have to look up.
I'd be curious. It seems like one of those things that has to be driven down a lot in order to get the kind of sensitivities you're working with.
Yeah, so I think I wouldn't be wrong if I said the two LIGO detectors are probably the most frequency, like sharp and frequency stabilized light sources that we have in the world. And I think the vacuum system we have probably compares only to the LHC. We might have exceeded them. I'm not 100% sure.
I'm nearby BNL. I don't know if you're familiar with them, but you know, in comparison, I'm sure LIGO has a much more advanced setup.
Yeah, I can look up the line width for you and I'll DM it to you.
Appreciate it, man. Thank you again for the talk.
All right. Okay, here's the link to that video if anyone's curious. And this is a really interesting video that someone made in like in 2016 or 15 to just show how the interferometer works and how that wiggling actually gives you the signal that Jester was after. And the sound clips. Oh, actually, that is more important. Can you paste sound in Discord chat? Because
You
I have the
can.
WAV files.
Yeah, you can just paste it.
Oh, wait, then I'll just do this. Downloads. It was this one, right? Let me double check. Yes, it is. Okay. So this is where the Discord go. This is what the theoretical sound should look like, or sound like. And you can see it's like a whoop sound. And if you want to hear the actual signal from the first detection that we had, GW, I have that somewhere as well on a YouTube video. Oh, no, wait, I can find it from my. Wait, do we have any other questions? Sorry, I'm tabbed out, so I can't see.
No. Well, actually, here, Quick and Smart has a question here. As someone who has little understanding of what's going on in this field, is there some game-changing research or findings being done, or right now or soon, that you think the average person should be aware of, paying attention to? I guess that kind of relates to the question that I have: is what you're looking for stuff. What
Yeah.
what are you gonna find that's gonna be like that changes how we think about the world? And if it's something that's fine, but like
That's
I'm
actually
curious.
a very good question because I kind of like gave you a very bad hand wavy reason for why we are measuring these. I mean, yeah, multi-message astronomy, but who cares? There's no good answer for that. A very philosophical answer that I can give you is, so normally when you're on like the edges of our scientific understanding, there's not much reason to do things, right? Because technology always kind of lags behind science by like a few years. An example that I can give you is, in fact, silicon. So when silicon was first, like the weird, funky characteristics of silicon when it comes to electrical stuff came into picture, people shunned it away as like a horrible conductor because at that time they were just looking for good metals and alloys that would have low resistance and like low losses when they're transmitting power to your houses, right? That's what people look for. And someone brought in silicon and like, this is dog shit. It's like almost as bad as wood in conducting, and throw it away. Luckily, some people still like stood by it and like did research, and now we can play Fortnite because of that. So it's very difficult to say what I would. I wouldn't say it's difficult to say. I don't want to say what this could lead to, because we are basically fiddling around with general relativity, right? Now people might tell you that, oh yeah, this is gonna like give us a better understanding of GR, and like we will have like faster than light travel and like warp technology and stuff later on because of this. No, I'm not gonna say that. All of that is mostly science fiction. Um, but it is gravitational waves are, as of now, the only direct measurements we can do of black holes. And the best answer I can give you for that is these are events that we will never have happen on or near Earth. Well, hope not, because if it does, we'll all be dead. Because these are like huge, extreme events. If you look at those fact charts that were there in the last few slides, some of these black holes are traveling like 50-60% the speed of light. And these are stars, like 20-30 times the mass of the sun, moving that fast. That will never happen. Gravitational waves are the only way we can study these events. And by studying these events, we might find something, or like at least better our understanding of these fringe cases of our theories, that like, I don't know, 50, 100 years later, someone figures out a way to use, uh, build, I don't know, John Piter's theoretical time machine or something. But I'm very hesitant to say exactly how this will better our lives. Because as of now, to be 100% honest, it won't. It's just we are hoping that we find something which is useful later on.
Yeah, I think that's a lot of science. I don't think that's unique
Yeah,
to.
a lot of fringe science is that. Well, I shouldn't say fringe science. Science which is like on its edge, like Large Hadron Collider. Who cares what's happening when like two protons collide super fast? Technically, no one does, but we still want to do it so that we improve our understanding of the basic fundamentals of physics that we have.
Yeah, I feel like they're like kind of figuring out what questions they have to ask to make the next new technology. You know?
Yeah, yeah. There's I mean, Ludzi is probably the person to answer this. In fact, this question is pretty related to the last comic meme that I had on my thank you slide, which is just how pure something is. Because mathematicians in the past wanted more pure stuff. So things like number theory were considered pure because they have no real world application. And someone just cooks up like a funny, fancy form of mathematics and people do it for the fun of it. Those were considered pure maths. And calculus and stuff was considered like dirty because it could be used in the real world. Ugh. So, but now cryptography is number theory is used in cryptography, right? You would think that study of prime numbers would not have any use, but we use those in cryptography now. Another example, going back a little past, is non-Euclidean geometry for GR as well. Someone just decided, what if we have a world where parallel lines intersect and the angles of a triangle don't add up to be 180? And there was no use for math like that at that time, but people still did it. And turns out when GR came into picture, well, that's the world we live in, and it's very useful. So it's something like that. How frequently do black holes merge? Like you had almost 10 days apart, but is that uncommon? Okay, so fun story about that, right? Like I'm gonna spend like 2 minutes to tell this story. The
Go
first
ahead.
detection we had, probably the loudest, one of the loudest, if not the loudest event we have ever had. And that technically happened when we were not even open, right? We were doing science runs, which are like test runs before the official observation starts, just to make sure that the detector is working or not. And this was like, I think we turned it on in the evening or like the afternoon, and it happened in the evening, something like that. It was like within a day or so. It was really soon, just as we turned on. We almost missed it. And it was the loudest we've had. In fact, it was so shocking that we did not talk about it. Well, I wasn't a part of the inner circle, but the people in the inner circle did not talk about it, did not publish anything. And everyone just like got into a room and started pointing fingers at each other, like, did you do this? Did you do this? Because people used to do that. They used to do these secretive injection runs. Like someone would go in and jostle something in a very specific way that would look like a signal, and then just test whether our systems were good enough to catch that. And everyone basically got into a room, pointed their fingers at each other, and asked, "Did you do it? Did you do it?" And everyone said, "Like I didn't." So it must be a signal. And very carefully they published the first event just to make sure, because it was that uncanny. And then we never saw a signal that loud. Coming back to the question though, how common are these? So these depend on, we have like numbers for how often these events might happen in like an area. So the larger you make that area of your detection, the more frequent they are. Right now, we actually see an event almost every day, but a lot of these events are not, we are just not clean and good enough that we can extract science out of it, like data, like how big the black holes were, how fast they were spinning. So if they are very close to the noise floor, we don't get any useful data out of it. So sometimes we don't publish these data. They are like uncategorized. If you look up like a list of events, anything that has GW before it, that's a gravitational wave. So that has been like statistically proven that this is probably a gravitational event. Everything will have like a false rate. I think it's called false rate probability. It's like, what is the probability of this just being noise? Like this noise just happened to be in the right time at the right place and it looked like a detection. If something is like 1 in a million or something, that's probably a signal. Right now we get about one signal every 1 or 2 weeks, which is like really good, and we're confident it is. We get about, I would say, like 2 to 3 a week, which are doubtful. Like we're not 100% sure whether they are or not. So we still like do a little bit of science, but we don't publish them in our catalogs. Otherwise, an event detection happens almost daily, if not multiple times a day. With the current generation of detectors that we have, we have done a lot of. This is the third generation of detectors, and we will soon have A sharp, which is the fourth. So black holes are merging constantly, even in our galaxy. And the rate goes up as we make our detectors better and increase the range of our detection, if that answers your question.
So, Kelly, I understand that you are. I mean, this is a lot of the research side of it. What are you doing, what are you doing for your job, like in this
Okay.
field?
Yes. So the LIGO collaboration, the US is called the LSC, LIGO Scientific Collaboration. I think that has like a few thousand professors. Like total group is like I think close to 10,000 if I'm not wrong. So it's a huge collaboration, right? And the systems are so complicated that you need like hundreds of people working on the same thing. The very specific to get a little technical, the things I specifically do is I mentioned that camera. So we have these lasers and they go through these beam splitters and mirrors, which are huge. Now, if you have, let's say, you won't, but if you had like a dust speck on this laser, we have almost a megawatt of laser light resonant in these arms. So that is just that speck is gonna burn. It's gonna cause a spot on the mirror, and that spot now is not the mirror, so it's gonna absorb this huge power of light falling on it. It'll heat up. Once it heats up, it's gonna distort the mirror. The mirror gets distorted. That's gonna change the shape of the laser beam. It's gonna cause a lot of problems for us. So the camera I'm working on specifically is supposed to look at the spot of this beam that comes out of the detector, and it can detect these distortions caused by these mirrors on the beam spot. And uh, and yeah, like if you see these distortions, you can probably like pick up the camera, put it somewhere else, and see if the distortion is there or not, and you can narrow down what is the faulty component that's causing the distortion. So that's what I'm working on right now. The other things I've worked on before are I mentioned the coatings. So we measure coating thermal noise. Now, if you a good question that you might have is if you're measuring distances which are 100 times smaller than a proton, atoms in the mirror vibrate much more than that, right? Like if atoms have, if they are not at 0 Kelvin, they will be moving, vibrating around. That vibration is much, much, much larger than the distances we measure. So how are we measuring something smaller than the vibration of the atoms in the mirror itself? And we do that by a lot of things. One of the things that categorize that is coating thermal noise, which is just the noise because of the vibration of the coating with temperature. And I measure that. I have like experiments that I designed to measure these coating noises and find coatings which are low noise. And that's basically the two big things that I did that I've done in my PhD so far. Otherwise, I mostly work with optics and electronics.
And why did you decide to get into the field? Like, what interests you in it?
Uh, doesn't really. It wasn't a question of interest, more so right place at the right time. Because I like as I mentioned, I was doing an engineering degree, and I was like clinically depressed by like my junior year. Like I hated. I didn't want to go to any classes. I was sitting at. I basically did the Atriarch, and I used to spend all of my time playing Dota. And somewhere around my third year, I kind of like realized that I don't want to do like a normal engineering job. I want to do research. By the way, keep in mind this was me at like 20, 21 years of age. So I have completely done a 180. I would kill to get a like a bog standard 9 to 5 desktop job right now. Like nothing makes me happier than like thinking of like just crunching numbers into an Excel spreadsheet and not thinking at all. But this was young me, a delusional me. So I thought I'm going to get into research. And I just happened to be in a university at a time where there was a conference about LIGO and gravitational waves. And at the time, yeah, like this looks interesting. And I like optics and I have an electrical engineering background. So I just got into it. I also have always liked physics from high school. So yeah, it was just, and as I kept working in it, I enjoyed it more and more. And I'm about to finish my 5th year. I probably have another year. If I get my wish, I'll probably stay for another 2, but my professor will probably kick me out by the end of this year.
And it's not related, but what do you enjoy most about working in this field? What's your favorite thing to be doing?
Uh, Okay, so this is probably a bit generic and valid for any research job. It's the fact that you don't really have a handbook, right? Like, uh, if you wake up in the morning, you don't you know what you're gonna do for that day, but you don't have a timetable, right? Like you don't have like, okay, I have to do this thing by the end of the day. You can go in and then you can find out, oh, this thing that I built last night is not working or it's not doing what I wanted it to do, and then you have to like go down a path of like figuring out what it is. And generally, if you're doing a PhD uh, in any subject, you are probably one of the most knowledgeable person in the field you're working in the world. So there's not a lot of people you can like just call up or email or meet and then ask like, oh, what's the problem, and they tell you what the problem is and you fix it. So you have to do a lot of it's just it's like an adventure in your job, and I like that. Well, correction, I liked that. Eat past tense. Now I'm kind of getting fed up with it. I want like a little bit of stability where I know what I will do the day and that I know that I'm going to be back home by 5 p.m. or at 5 p.m. or whatever. It's very common for grad students to like work the weekends as well just because they couldn't figure something out for 2 days, Thursday and Friday. But yeah, that's a positive and a negative. Depends on how you take it. But that's what I like most.
All right, and I guess the last question here. If someone was interested in getting into this kind of field of gravitational waves and just this in general, I think there's a pretty clear path. What would you say they should be doing? What should they should be studying? What should they be doing right now?
Okay. So very specifically gravitational waves, we broadly have three areas of in the collaboration. Four actually, correction. One is theory, which is just theory, like the theory people who do GR and stuff. I don't really know what they do. I don't interact with them a lot. Then there's the experimental people, which is me and the likes of me. We do research on the instrument. Almost all of the work is experimental. You're in a lab working. Uh, a lot of this is optics because it is an optical device like detector after all. But we have people working with seismic noises. We have like geologists who do seismic noise studies to understand how that is. We have material science people doing coatings and stuff. We have vacuum specialists who work on the vacuum systems. Uh, a lot of these people, and then kind of adjacent to these are the technical people, like technicians. They don't really do research, but they like work at the detectors, and they are the ones who actually like build things. So while we like are in the universities in a lab doing stuff, they are the ones at the detectors who like maintain stuff and all. But that's like a very small group. And then we have the data scientists, which is probably the biggest group. And these are the people who make these mathematical models and they grab the data uh, and do some magic with it and give us like like science out of it. I'm not 100% sure. I've heard machine learning, I've heard parameter fitting, I've heard these terms, but I don't know what they do. It's data science, but like we have like a big data science group, or like a random number that I remember. I don't know from where, but one of these big detectors we had, the number of CPU hours that required was the equivalent of like running like 30,000 or something computers for like a year or something stupid like that. And like we use supercomputers to do a lot of these fittings and stuff. And the uh, most challenging part of that is doing this quick. We don't really have a lot of time. If a gravitational wave, for example, the neutron star gravitational wave, we have seconds or minutes before we want like a alarm to go off somewhere and then send alerts to optics people who can point their telescopes at that part of the sky. So a lot of this needs to be fast and uh, beefy. I don't know what the term is. So a big group is the data science people. So one of these three, theory, experimental, and data, which is a bit weird to say because that's almost everything. But yeah, these are the three areas that we have where if you're interested, you can get in. And if it is just graduate school in general, it's like just be unemployed after you finish your college. You'll eventually get into grad school.